Okay, Friday, January 26th, 2024. Let's go to the second. Let's cover the second part of the of this week's lecture, which is the coaxial cable. We covered characteristic impedance, well, impedance and characteristic impedance last time we saw each other in person, and today we're going to continue with the signal routing, and well, which we're going to talk about how the signal travels through the coaxial cable, and we're going to talk about the differences between the broadband transmission and the baseband transmission. Okay, so but before we start, I'm going to bring the course plan here. So week 4, January 22nd to January 26th. So we're talking about coaxial cable, signal multiplexing. Look at this thing. Week 5 is going to be the first test, and the test is going to be same as my tests were last semester with the other class, which was the safety 1051. Okay. And I'm going to release the test sometime this weekend, and it's going to be on the same basis that last time. So you'll have a few days to do it. Now, are we going to have some classes? I'm going to see if there is anything that I need to add as a supplement in order for you to get as much as possible. And if there is something that I need to add, then I'm going to put that in the announcements. So probably there won't be any classes, but there's always that but. So look for the announcements, okay? All right. So that's as far as that. Now, this was the presentation last time we had, and that was the... There we go. That was the last slide that we had. Now, let me just bring it to the full screen. Control L. I think that's the full screen thing. All right. So just as a review, what did we establish? We established that when we are connecting a capacitor in series in a circuit and we put AC source, alternating current source, we get a little bit different effect that if we put the inductor or coil or a solenoid, or same thing, in the circuit. Right? Just as a quick review, here's the power supply voltage. Right? Now let's see, this one is 0. So it's not really alternating current, but it's the changing situation happening here. This could be called, this could be considered as pulsating DC if this is a 0. Right? But it could be also, if the 0 was in the middle, then it would be alternating current. However, we have enough changes to go by. All right. If we connect the capacitor, look what happens. Here's the power supply voltage, and here's the power supply voltage. If we connect the capacitor in series and we introduce a change all of a sudden, then what did I say last time? Capacitors love change. They just love change. Coils hate change, right? Now, all of a sudden there's a change. Capacitor loves it. It's going to start conducting current right away because capacitor loves change. It will start conducting. Why is it conducting? It's because if it's discharged, it is going to start charging. So it's going to give us the maximum available current that's possible in this circuit, considering the resistor being in the circuit, and it's going to start charging. As it charges, right, then the current is going to slow down because it's not going to charge as much as it before because it's getting to, it's getting filled up, right? And the current is going to go less and less and less and less. And as the current goes down, it becomes more resistive. So that means the voltage are going to start appearing. And, when the current stops completely here, then we're going to have the maximum available voltage. So in capacitors, when we have capacitor in the circuit, it is going to conduct current first, and the voltage is going to appear. So current leads the voltage. And coil is a different thing. So we have a change. Coils do not like change. So at the beginning, it is going to be as resistive as possible. So it's not going to conduct current. And as there is no change further on, coil is going to say, okay, if you settle down, I'll talk to you, right? Then it's going to slowly start conducting current. But if there's no current, so basically the resistance is maximum. So if the resistance is maximum here, then the voltage is going to be maximum, right? The more resistance you have in a circuit, the more voltage drop you're going to have across that component. So it's just the opposite of that. Now, we talked about the resonant frequency, and you know what? I'm going to make a separate video on the resonant frequency, just for the sake of doing it, just so you can understand the electric kitty a little bit better, right? Electricity, okay? Because the voltages and currents behave differently in the coils, so then in one capacitor, the voltage goes second, and in the coil, the voltage goes first. So we could say that if you connect the oscilloscope, they are going to appear 180 degrees out of phase comparing to each other. That's an interesting thing here, right? Because look, here is we're still doing a bit of a review here. Here is the inductive reactance, XL, and here is the capacitive reactance, XC. Why is this thing here on the top, and why is this thing here on the bottom? Well, what's a reactance? It's a form of a resistance. It's a reactive resistance, but it is a resistance. Right? So when voltage appears first on the coil, that means there is a maximum resistance. So the resistance is going to be ahead of this zero angle here. And in capacitor, voltage comes second to the current, then it is going to follow that the opposite way. You might want to review this. You might want to pause it, and well, if you're watching on YouTube, you might want to kind of stop here and try to understand why these are here. Just make sure you understand that, right? But that's the way things are. Reactance, inductive reactance is going to be pointing up as a vector, and because it's first, and then the current happens in resistance. In the resistor, the current and voltage are in phase. There's no difference. And coil, voltage leads, which means voltage goes with the resistance. More resistance, the more voltage you have. In capacitor, voltage lags. So then it's just the opposite. And it manifests itself, right, just like a mirror image of voltages on the scope, right? Now, what happens if we have across the capacitor and across the resistor, if we have the voltages opposite to each other? Remember we talked about the resonant frequency? At a certain point, if we have a certain specific value and a certain specific value for this particular values of the capacitor and the coil, the resonant frequency is going to be, well, about 50 hertz. So at 50 hertz, these voltages are going to be, well, not only 180 degrees apart from each other, but they will be of the same magnitudes. So what happens if we have voltage pointing this way and voltage pointing that way across this, and they're of the same magnitude, so they will cancel each other. So at the resonant frequency, if you have those two components in series, they're going to cancel each other out. So it's just like if they were not there. At the resonant frequency, the resistance of that, or the impedance of those two, the impedances are going to cancel each other. And it's just like if you throw them out and put a wire there. That's going to be, the resonant frequency. Why? Because they're same magnitudes, but they will have different angles. They will be opposite. They will be opposite each other, so they will cancel each other out. All right. So, and this was the last slide here. Oh, what about parallel? Aha. We got this thing here. If we have a parallel, okay, why not? Where's my board? Here. Okay. So if we have this thing in parallel, so here we have a source. Let's say, you know what? Let's say we have a DC source, for example. DC source. So here's plus, here's minus. Okay, and we have a capacitor, and we have a coil, and they are in parallel. Learn how to draw back. All right, there we go. Almost there. All right, so here is a thing going on, right? All right, let's get a switch as well. Boom. And a switch. So what happens if we press the switch? And if those values are, well, if there are certain values, we can calculate what the resonant frequency is going to be. So it doesn't matter what the frequency. Let's say same values that we had on that one. So that was there. Capacitor with 100 microfarads and inductor would be 100 millihenries. So then they will have the resonant frequency of 50 hertz. Okay, well, what's going to happen? Oops. We're going to get, come on. Yeah. That's what I want. All right. So we have this thing connected in parallel. Okay. So when we have the resonant frequency happening, the impedances of that are going to be opposite to each other. And what is going to happen is that there's going to be pretty much almost like a ring here. What that is going to accomplish is that the current is going to stop flowing because this one here, the current in the whole circuit, if we close the switch, this is called a tank circuit, just like the tanks in the army or the tanks of, tank of water, right? What's going to happen is that this part here is going to start oscillating back and forth. There's going to be current going back and forth, back and forth, back and forth at that frequency. So it's going to start oscillating. And because this is going to start oscillating, it'll stop the current at that 50 hertz. But if we just apply DC, we're going to create an oscillator. That's it. This thing is going to self-excite because coil has something. If you suddenly apply voltage change, it is going to produce a ring, just like if you strike, some sort of, percussion timbal, or otherwise called plate, or a gong. You hit it with the with the stick, and it's going to go boom. So it's going to start ringing, and that's going to be enough to self-excite and start building up because there's a constant supply of power, and it's going to start oscillating. So you're going to create an oscillator of that frequency, right? So, and I should probably connect this thing on a multi-sim, maybe using real parts, and that's going to be fun to show. So in the parallel, you get a tank circuit. And it's get the opposite of the series, because in series it just conducts no problem, that frequency, 50 hertz, for example, and this one here is going to block the 50 hertz frequency, and that 50 hertz frequency is going to start oscillating within this tank circuit, right? There we go. So all right, so that was the last slide here. We had conductance, capacitance, and inductance. It's part of every single part, electronic part that exists. Everything will have conductance because conductance is the opposite of resistance. So if it has a conductance, it will have a resistance. Any kind of electronic part or anything that we connect. It will have capacitance. It will have inductance. Now, how much of which it is going to have, it is how, what the purpose of the part is and how it is built for the purpose. So if it's a capacitor, the dominant quality of that is going to be capacitance. And it's going to have a little bit of inductance because we just can't escape it, but it's going to be so little, so insignificant that we can just say that it's zero, but it's still going to have a little tiny bit of it, right? And it's going to have conductance, it's going to have resistance. So if it has conductance, it will have resistance. If it has capacitance, it will have capacitive reactance, and that has inductive reactance, right? And because it has all three, and it will have impedance, right? Now, I wonder if you remember the question that I asked you last time we saw each other. It was, why do we need to make sure that we match the impedances between two things when we connect things, right? Remember when we insert, the way we use the cable is that the amplifier is going to insert a wave, is going to shoot the wave down this opening here, and the wave is going to travel on its own. Once the wave inserted into the cable, it just travels on its own. Same as if you drop a little stone in the water. The important moment is, the significant moment of that is when the stone hits the surface of the water and creates the waves. Then it just sinks to the bottom and it has no play in the picture whatsoever. It's out of the picture, but the waves continue on their own. Right? So what we are considering here is how hard it is to throw that rock into the water. How hard is it going to hit the water? So if it comes to water, we're going to say, okay, what's the density of the water? What's the consistency? Is it salty? Is it not? All the physical aspects of that. And that is going to just be important at the moment of contact. And that's it. So I'm getting somewhere with this. All right, don't worry. Here's a couple of things that if you want to continue with self-educating, or maybe you will need that in other subjects, you might want to research what permittivity is and relative permittivity. Permittivity is the resistance to the electric field, and it's in farads per meter. And relative permittivity is permittivity of a material compared to the permittivity of the vacuum. Just gonna leave you with that. I'm not gonna be on a test. I'm just pointing you in some things that relate to these, right? Now, that has to do with the way the coaxial cable is built. Now, here's the characteristic impedance. Here's the formula for that. I'm not going to analyze and derive the formula because that would be, it's a little bit of a complex process. But out of everything that you see here, is there anything that would suggest that the characteristic impedance would depend on the total length of the cable? No. What comes in play? Well, here's the K is a constant, so it's a relative permittivity of the insulation between the conductors. There you go, see? There you go, right? And here is the distance, the diameter, the inside diameter of the outer conductor, and there's the outside diameter of the inner conductor. That's the whole thing that's just in the formula. And that, based on that, we can calculate the characteristic impedance. So based on, just by looking at this formula, you can tell that the total length of the cable it makes no difference. So in fact, the characteristic impedance of a coaxial cable is the pretty much impedance of the cable of the first meter of the cable. That determines how hard or how easy it is to insert the wave into the cable, and so that wave can travel on its own. Now, why is it important that the impedances match? The two most common impedances, by the way, in coaxial cables are 50 ohms and 75 ohms. So if there is, let me bring my board back. There we go. I'm going to start using tabs as suggested before. All right, here's a new tab. There you go. Thank you, Jay. All right. So what were we talking about? Impedances. Why is it important that the impedances are matched? And as much as it's not my favorite thing to do, to compare electricity to water, but sometimes that's all we have in order to give you the best kind of explanation. All right, so let's say we have two pipes of water. Here's one pipe, and here's the other pipe, and they are the same diameter, same everything. Right? So here's water flowing, okay, water flowing with certain pressure, certain volume per whatever. And if we want to continue that flow with the same specifications, well, we're going to get the same pipe and we're going to join that, and the water will never know the difference. It's just going to continue traveling as it was, as it were. Okay. Now, if we have another situation where there is a pipe and there's going to be another pipe which is smaller and it's going to be connected to that, and there's a water flowing here, water, with a certain volume, certain speed, and what's going to happen here, because that's going to be closed, and it's just going to be that opening here. Well, some of the water is going to bounce back from this interface here. It's going to be a turmoil, and you're going to have some flow, but you're not going to have exactly the same flow. All right, so that's if the impedances were mismatched. Let's say we have another situation. We have a thin pipe on this side, and we have a thicker pipe on this side here. Okay, what's going to happen? Are we going to have the same type of flow? No, because the water is just going to start gathering on the bottom, and it's going to fill this pipe up, and then we're going to have some flow over there. So we're not going to have the same kind of a signal transfer. All right. Next tab. There we go. If we have a amplifier that is specified for 75 ohms, right, then you better get a cable that is specified with 75 ohms of what? 75 ohms of the characteristic impedance, because we're talking inserting waves into the cable, right? All right, oh, that's a very crappy looking omega thing. Now that is going to be connected to a antenna that is also will be having 75 ohms impedance. So here is the output impedance of that, the input or characteristic, and here's the impedance, and here's impedance. We got the same amount of same impedance. The impedances are matched. Why do we do that? There are three words that are the answer to that, and it's called maximum power transfer. Right? Here, let me write it so you can get this. Lorem ipsum, okay. Maximum power transfer. That's the idea. That's why we need to match the impedances. Otherwise, if you have mismatched impedances, some of the power is going to bounce back and it's going to dissipate as heat in the amplifier, or it's just going to heat up the cable, but cable's not going to heat much. But that's what's going to happen. So that's one thing. You can actually damage the amplifier. Plus, you are not going to have the signal strength that you want. You're going to have the signal strength that you actually don't want, and it's enough to make a difference that is going to be a problem. If you have 50 ohm characteristic impedance cable, then you need to get, if you have a 50 ohm amplifier, then you're going to get, or the transmitter, which is the amplifier on the end, it's a radio frequency amplifier, and you need to match, everything has to be 50 ohms. Right? There are two basic characteristic impedances for the coaxial cables: 50 ohms or 75 ohms. That's it. Right? Unless there's something I don't know. All right, let's all right, so a couple of questions. Will the characteristic impedance change if the total length of the coaxial cable changes? Yes or no? No. There we go. We got one. Anybody else? Everybody sleeping? How many people we have? We have 32 people. All right, we got there. Okay. All right, good. That's correct. Now, why do we need to match the impedances as we interface different parts of the whole transmission system? That's a kind of the flow will be mismatched. There you go. Maximum power transfer. 3 words. Good. Got it. I taught you something this year. There's another thing I taught you. What day is it today? Well, actually, today is not almost Friday. It's actually Friday, so it doesn't. All right. Let's take a look at some of the designations for the coaxial cables. There we have contestant number 1 in the middle, RG6. Then we have to the right, we have RG11 and RG59. Those numbers, they don't mean anything. They are just used for the cataloging purposes of certain cables that were developed for certain purposes. And then we also have RG58. All right. Let's look at some of the specifications. All right, RG6 uses cable television. It was mostly in the past, unless there is some remote places in the world that still use the cable television, but now everything is digital. CCTV, excuse me. CCTV stands for closed circuit television system. And if you remember, for some of your high schools, they will have a bunch of TVs in the classrooms, and maybe every Friday the broadcasting class would broadcast their broadcasts, announcements, and they would produce a bunch of things, news and weather and features and stuff like that. So those TVs were connected through this closed circuit television system. Now things are, some schools are still using that, some not anymore. This digital, so there's a bit of a transition going on right now, right? That RG6 cable, and this is also the one that you see if you have internet brought to you by cable, but so-called cable, that's the RG6, and that's the thickness of RG6. RG59 is thinner, RG11 is much thicker. Right? So to provide internet, and here is the thing, I put it in orange, broadband. It's because we don't know what broadband is yet, but we will know in about 2 or 3 slides further down the road here. So today, before the sun comes down, you will know what broadband is. Okay, there we go. And it's being used for antennas. So it is, right? Yeah, there you go. Now, I just put that thing here, frequency limit, 1000 megahertz. Why didn't I just say 1 gigahertz? Because 1 gigahertz is 1000 megahertz. It's because in the industry, in just a popular way of communicating, people are using megahertz So even if it's 1 gigahertz, just people are communicating with megahertz. It's just the way kind of things have settled, all right? And characteristic impedance 75 ohms. All right, RG11. Well, what does it have? RG11 mostly for cable television, same uses. But look at this thing here. Frequency limit is 3000 megahertz instead of 1000. It's 3 times, so it's got a better bandwidth. What does that mean? That means that you can have, in this one here, RG6, you can have a signal that is up to 1000 megahertz in frequency, and you can transmit that signal as something useful. So it can carry the signal in a way that it will be understood at the other end. It's not going to be garbled, okay? Or sometimes it just doesn't get there at all. Now, RG11 cable can transmit the signal of, has more bandwidth, right? Transmit signal of 3 times more frequency. So, it can carry more data here, right? Or more content. Now, look at this thing here. RG59 was used to connect the computers, networks, but that was in the past. Video signals for the security cameras, also mostly in the past. However, there are still some of those analog cameras installed. And because there are still a lot of them installed, there are still a lot of them working, and with the cable infrastructure going on, still some of the head end, the analog head end that handles the analog cameras, is still being produced for that purpose, because people still have them, and it will be too much money, it will be too expensive to replace all the cabling, but maybe the hard drive has gone bad or something like that. So those are still being produced. Amateur radio still in use. RG59. Frequency limit 1000 megahertz. Well, same as that one. Then what gives? What makes this thing different? Characteristic impedance 75 ohms. 75 ohms. The differences are in the next slide. All right. So hang tight. And then also we have the RG58. And it's mostly used for the amateur radio antennas. The frequency limit is 5000 megahertz, so it's even more than the RG11, right? But the characteristic impedance is 50 ohms, so it's mostly being used. RG58 is probably the most popular cable that connects the transmitter and receiver, or transceiver, to the antennas when used in amateur radio, the shortwave enthusiasts. Okay, it's still going relatively strong, right? Not as strong as in 50s, 60s, 70s, right? The shortwave is that was really booming. Now but it's still going on. Right? All right, so let's move to the next slide, because we want to come out. We want to. Okay, here's the link. Click on that when you download it to find out a bit of a history, technical history of why is it 50 ohms that is actually being used. Not gonna ask you any questions on that. Why is it 50 ohms? But I might ask you some questions on this here. Right. All right. So, what is the difference between? Why do we have differences? Why do we have two different designations? Physically, they are different cables. This one is thicker. This one is a little bit thinner. So that should tell you a little bit something almost right now. Look at this table here. Here we have 3 contestants: RG59, RG6, RG11, and here are the frequencies. And what we have here is the attenuation, and at 68, well, at 20 degrees Celsius, so it's just a secondary information here, right? Under normal circumstances, right? So if you go to Siberia and try to install, which is cold over there, cable might behave a little bit different. All right, normal circumstances, attenuation. What's attenuation? Attenuation is a signal deterioration, making the signal smaller, making the signal lose energy. Okay. All right. So we have dB per 100 feet. And in the same here, just so you know, the dB per 100 meters. But let's concentrate, just, for the simplicity purposes, we're going to concentrate on the feet, dBs per feet. Well, what is the dBs? What's up with this? Yeah. Well, one thing I'm going to tell you about that, it's the decibel scale. It's a referential scale. So if you have a decibel, it's always compared to something. It could be compared to something standard, like if you say 1 dBm or 10 dBms, then it is comparing the signal to milliwatt. dB and the answers for milliwatt. For example, if we're talking about power, but we're talking about the signal loss. So it's going to be the signal loss. If the signal is being at the output of an amplifier, and if we have a cable RG59 connected, and if we measure the signal at 100 feet further down the road, further down the length, we're going to have a signal that is going to be 0.89 dBs attenuated per 100 feet. Now, if the frequency goes up, if you notice, the attenuation goes up. So that's the signal comparing from one to another, from the output to the input. It's a comparison. How are things calculated? We're not going to get into it, but I'm going to tell you a couple of general rules when it comes to the decibels. If you're dealing with power, and if you have any kind of power, so it could be a power of the signal traveling through the cable, or it could be a power of a sound coming out of the stereo speakers. So if there's a sound, for example, coming out of a stereo speaker, and you double the power of the sound coming out of the speaker, you have raised the power by 3 decibels. So if you have a signal coming out of the speaker is 100 watts, you raise that signal by 3 decibels, you have 200 watts. Now you raise that by 3 decibels, you get 400 watts. You raise that by 3 decibels, you get 800 watts. That's how it goes. So, and then it goes the other way too. If you have a 100-watt signal, and if you lower that by 3 decibels, then you get 50 watts. You lower that by 3 decibels, you get 25 watts, and so on. That's when power. Now, sometimes you're going to be dealing with the oscilloscopes, and maybe in some labs further down the road for during your education, you're going to be asked to raise the voltage by 6 decibels. If you raise the voltage by 6 decibels, you're doubling the voltage. So it's different. There are 2 different numbers. If it comes to power, the magic number is 3. When it comes to voltage, the magic number is 6. So if you raise voltage by 6 dBs, you're doubling the voltage. Or if you're lowering the voltage by 6 dBs, you're cutting the voltage in half, and so on. The purpose of this logarithmic scale has to do with the logarithmic calculations, is so we could plot graphs on a regular sheet of paper, like 8.5 by 11, that normally, if you didn't use the decibel scale, it would take you maybe 2 kilometers to plot the same thing. So all right, so now we're dealing with power. So now you have some kind of a reference when it comes to the decibels here per 100 feet. All right. So per every 100 feet, it's going to be attenuated by 0.89 dBs. And now look at this. As the frequency increases, the attenuation goes up. So it looks like in the coaxial cable, signals with higher frequencies get attenuated more, which means the higher frequencies do not have as much of a punch power while traveling through the cable as the low frequencies do. Right. Now, See the difference between, where's the table here that we had? Come on. There you go. You see, the bandwidth, it can carry the same frequency and the signal still can be understood while traveling through this type of cable, 1000 megahertz up to 1000 megahertz as well. Same characteristic impedance. All right. What makes it different? RG59 is not as efficient as transferring the signal as RG6 is. And that is not as efficient as RG11 is. Let's look at, let's see, around 200 megahertz. RG59 is going to attenuate the signal by almost, 3.5 dB. RG6 only 2.87 dBs, same signal. And RG11 is going to deteriorate only by almost 2. Right? So that's, now of course, this is the most expensive cable. This is the mediocre type of thing between these three, and this is the least expensive cable. Why do we have different cables? Well, you got your answer right now. All right. Now, when you're dealing with buying maybe 100 feet or 200, even 500 feet of cable, then you're not going to feel as much of a difference when you have to pay. But if you have to, buy 20, 30, 40,000 feet of the cable, well, then it makes a difference. All right. Now, this one here is just to get you some kind of a visual on how the old TV channels, the analog signal was distributed. So here's channel 2 of the TV, 3, 4, 5, and 6, 7, 8, and up to 13. And it was something that's called VHF, the low band of the VHF. VHF stands for very high frequencies, and it is, each channel would get 6 megahertz of bandwidth to transmit the content. So channel 2 is the lowest one on the TV spectrum, and it will go from 54 to 60 megahertz. Right? Then channel 3, another 6 megahertz of space to shove all the content, and 60 to 66, and so on. Every 6 megahertz, you will have we'll have another channel. Then channel 7, and then there's those other signals. If you want to, I have somewhere here. When you download it, you can click on this link, and you're going to see the North American television frequencies when it comes to TVs. All right. Not gonna ask you that on question on the test, but just so you know that something like that did exist. Now, the internet is being transmitted in the form of broadband. Okay, now here's something that's called a radio frequency amplifier, RF amplifier. Very simple as far as operation. Right? Not a rocket science here. We have an input and we have an output. That's it. As far as connections. This one here is a test. If you can just grab a sample of what's coming in. And over here is the output test, so you can grab a sample of what's coming out. Now, notice because of normally when the signal comes from the city, from outside the building, it gets strong. Maybe 20 dBs, maybe 40 dBs, whichever the strength of the signal comes in. If you wanted to connect straight to TV tuner, it would be too strong for the TV. So the signal will be displayed not properly, and if it's too strong, it might actually get, tuner might get damaged. Right? So if you want to kind of take a sample of what's coming in, you just connect your TV to this one here, because the signal is lowered by 20 dBs. What's inside, what's on the input, and over here, same thing. What's on the output lowered by 20 dBs, and you get your test sample of on the output. So now this one here, connect TV here, so there's something coming in, and actually the amplifier works because there's something coming out. Excuse me. Now we have two controls. One is gain, so it's just like a volume control in your car stereo. So, but this is for gain for the volume, for the video signal, or the frequencies, modulated frequencies, channels. And here's some kind of a mysterious thing that says tilt. Sometimes it's called a slope. All right. Look at this table. Per 100 feet, just one of them. As the frequency goes up, so as you go up with the channels, the signal is not being transmitted as efficiently as the lower channels. It could be a huge difference. Look, 0.89 dBs at 5 megahertz of attenuation compared to 16. Well, remember, if you lower it by 3 dB, you're cutting the power in half, but this is 16 dBs. That's wow, you know. So, what the problem could be is if you have an amplifier, come on. I'm getting some messages here. There we go. If we have an amplifier and we have a long transmission line here, so that would be the RG11 to carry most of the signal. And from there, you're going to go to, let's say it's a school. So that goes TV to the classroom, TV to a classroom, TV to a classroom, and so on. And that could be long hallway, and this could be another TV at the last classroom. So you're going to find that over here, at the beginning of the run, you're going to get proper signal strength all across all the TV channels, from the low channels to the high channels. But if you go to the very end of the hallway, far, maybe 200, 300 feet, 500 feet, you're going to see, the low channels are coming pretty good, but the high channels are snowy and it seems like there's a weak signal going on. Well, that's because the coaxial cable attenuates higher frequencies more than the lower frequencies. The lower frequencies have enough power to come through and travel. The higher frequencies don't have as much punch power to travel as far as the low frequencies can. So what we could do is we could adjust the way this amplifier works in a way that on this output, the higher frequencies are boosted more than the lower frequencies right at the start. So as the signal travels down the long cable, the higher frequencies have almost the same chance as the lower frequencies. So you adjust the gain, and you adjust the tilt, and you adjust the gain, and you adjust the tilt. Sometimes it takes you a few times to find the correct balance between these two, so you can have pretty much even signal distribution through the whole transmission line, right? If that's, for example, school and the CCTV going on there. All right, now let's keep going with this. We're almost done here, almost, but not yet. Last for dessert, broadband connection and the baseband connection. All right, broadband internet service is the most used form of internet access because of its high access speed. Broadband, don't worry, we'll get to it, what it actually is. Broadband is offered in 4 different forms: DSL, fiber optic, cable, or satellite. Yeah, pretty much. What's DSL? DSL is digital subscribers line, and that's the signal that is superimposed onto a telephone line. DSL travels through telephone line. through POTS, plain old telephone service. Before that, it was a dial-up connection. We'll talk about that too. So the dial-up connection was you connect the modem to a phone line, and when you want to connect to internet, you make the modem dial a phone number through a phone cable, and you get connected to whatever server is under that phone number, and you make a connection with the internet and blah blah blah. You can use the internet. It was slow comparing to what's today. Now there's some so-called high-speed internet. DSL is considered still high-speed internet. Well, with a grain of salt anymore, right? That also brings me to explaining something like the concept of a dry loop. Okay, what happens is that because the infrastructure was laid out pretty well, then somebody got a bright idea. Why don't we just, since we have this wiring already done, why don't we just superimpose the internet signal onto the POTS line, which is plain old telephone service, which is the telephone line. And then we can have two signals. You can have voice and data on the same pair of cable. And you can use the phone at the same time as you use the internet. Cool idea, right? Yeah, okay, well, it is. The only problem was that when you picked up the phone and you want to talk to someone, you would hear that annoying buzzing sound because of the signal from the internet. So no problem. You could get the POTS filters, and the filter, you would have to plug in a filter to the telephone outlet, and then you plug in a telephone to the filter. It would filter out the annoying buzzing noise, and you could still use the telephone as it were. It was no difference. Or you could get one. So if you had 2 or 3 phones in your house, then you would have to plug in the filter to every single one of them, right? So you would need 3 filters. Or you can have one main filter that you could plug into the at the demarcation point, which is at the point of entry. You plug in the line as it comes into the building, straight into the filter, and it filters things out. So part of the signal gets connected to the modem, and it only has the internet signal, and the other output of that filter has just a telephone voice thing, and that connects to the rest of the house's phones. In this case, you don't need the filter at every single phone, right? So these are the POTS filters. Now, what is a dry loop? Right. A dry loop is that at some point, people decided, well, the cell phones, you're talking about beginning of the year 2000s kind of a thing, right? The beginning of the millennium. The cell phones became so popular that everybody in the household would have a cell phone, so there was no more need for a one common landline telephone. You don't need a phone in the kitchen anymore, or in the, somewhere in the foyer or in the living room, because who cares? Everybody has their own cell phone anyways, right? But the signal infrastructure was there, and you still wanted to have an internet through the same cable. So somebody called and said, look, is it possible to not pay for the phone, but still have the internet signal, the DSL signal being transmitted through the same phone lines? So that was called a dry loop. When there's just through the phone lines, the voice circuitry, the phone will be disconnected at the city side, the central office side, but the telephone wire would carry only the DSL signal. So it's called a dry loop. Not to be confused with the hard loop. A hard loop is a diagnostic circuit, and it's used to test the Ethernet links. For example, it's like Ethernet link uses, Cat5e uses 2 pairs, orange and green. One is transmit, one is receive, and it's connected to whatever device, and in a way that both pairs can receive and transmit signals accordingly, and it's connected to the circuitry of one device and the other. But in order to test the line, you can plug in something that's called a hard loop, and a hard loop is just a Ethernet plug with those transmit pairs and the receive pair just coupled to each other. So transmit pair goes right, loops up in about 2 inches of length or maybe half an inch, and goes right back into the receive line. So it's like a loop. And that could be used as a diagnostic tool to test the specifications of the line, right? So that's a hard loop. Dry loop is a telephone line that carries only DSL signal, no voice circuitry. All right. So the broadband versus baseband. Right. Now, Ethernet signal is type of digital. That's best delivery time division multiplexing as a baseband. And internet, that's the signal coming from the outside, is an analog, and it uses frequency division multiplexing. Now let's talk about what those are. Broadband versus baseband. Connection is divided into connections are divided into channels. The best example, I'm going to a little bit go over time, so if you have to go, and you can catch the end of it when I post it, which is going to be right after the thing is done. I'm personally glad dial-up is not around. Actually, you know what? Dial-up is still around. I'll explain how. It's still around, but not for the regular internet use that we had. But it was, when I hear that modem noise, it's kind of sentimental. Yeah. All right. So, broadband versus baseband. The best way to describe broadband is the radio frequencies in the air. They're all there at the same time. What your car stereo does, if you want to listen to the radio, your tuner tunes to a specific frequency, and it tunes to that one frequency that it wants to listen from all the frequencies that are present at all time. Broadband transmission. All the frequencies are present. All the channels are present. All the content is present constantly in the air or in the cable, because cable can also carry radio transmission. In fact, coaxial cable is called radio guide, RG, to carry radio frequency channels. So if we have a cable, and I'm just going to put channel 1, 2, and 3 here, but there could be 100 or 200 channels. We have a multiplexer and we have a demultiplexer. All right, so here is the broadband. All the content is there at the same time. The purpose of the multiplexer is to combine all the signals that are coming in and put them into one big mishmash of frequencies and just shoot them down the pipes. The purpose of the demultiplexer is to fish out specific frequencies and direct them to specific channels, or maybe one channel if it's a car stereo, which is a simple demultiplexer. So that's the broadband. In this case, the link or a cable needs to have as much bandwidth as possible. So see that RG58 will be the best for that one because it has the 5,000 megahertz bandwidth. It can carry a lot of carriers. You can chop the bandwidth into many different sections. You can have many more channels than RG6, which is just 1,000 megahertz. Right? All right. Now we're going to go into the baseband transmission. It's constructed a little bit different. instead of having all the channels present in one link, we're going to have time sharing. And, well, let's say these are telephone conversations. Here's one telephone, here's another telephone conversation. So we have 4. There could be many, but it's just, let's just get 4. And say this phone is talking to that phone. This phone is talking to that phone. There's a conversation. We have 4 separate conversations. Here, can you see that? Now, let's say the multiplexer, you can imagine a big wheel with contacts on them. All right, thank you. You can, you can catch the rest of this when I post it on the internet and on our YouTube playlist. Okay. And if this wheel turns, making contact with one channel at a time, and whichever the contact touches, whichever channel the contact makes contact with, at that time, this channel is being transmitted through that one thinner link. And if there is another wheel that is synchronized in a timely manner with the other wheel, so if the contact touches the A on here, then the contact touches the A on the other wheel, so that channel is being transmitted at that time. And if it happens every second, you would have time sharing every 4 seconds. 1, 2, 3, 4. 1, 2, 3, 4. A would have a 1 second connection every 4 seconds. Well, that would be quite annoying if the wheel was spinning slow. But if those both wheels are spinning very fast, extremely fast, and if they are synchronized, then, well, you're going to have the illusion that those breaks between signal are going to be so short, so the conversation number A, excuse me, and for example, the conversation A, the people will have the illusion as if they had a dedicated line, because things are happening so fast. So that's the time division multiplexing. In this case, this cable doesn't have to have a huge bandwidth, but it has to be able to switch fast. Broadband transmission, time division, it's both multiplexing. So this one uses frequency division multiplexing. Things are on different frequencies. There is no tuner needed here. Well, as far as tuning, that tuner has to be tuned to that channel and period. That's it. This one here, the tuner can switch between channels that are being transmitted. Frequency division multiplexing in the broadband, time division multiplexing in the baseband. Multiplexing is switching between tasks in a timely and synchronized manner. All right. Now, here's for you, Jay. Dial-up connection. It's still being used. How did it work? Well, here's a computer at home. Here's a modem. Modem dials a phone number. The phone number is being recognized by the central office. It connects you to whatever local facility, whatever it is that the server is on. This connects to another central office, local exchange. That rings the phone, is automatically being picked up by a server, and this computer is connected to this server through a telephone line, and the communication is not very fast. is still being used. Now it's being phased out somewhat, but in some crucial, when you need some backup, it's still being used, the dial-up. This is a typical small business network equipment rack. What do we have? We have a patch panel here. From the patch panels, there is field wiring. What's a field? Field is the rest of the building. Right? So these cables are connected to individual jacks in the walls and whatnot, desktop, and they're connected to the patch panels, just bunch of dry connections between that jack and the jack in the field. From here, things are being patched to the switch on a one-to-one basis to the switch ports. There's some other patch panel for some other purpose, and those two switches could be connected to the gateway or another switch, and whichever it makes its way to the cloud, and the network works. The backup quite often is being used in the retail business. Mm-hmm. Let's say there's a store that has 6 cash registers, and all those cash registers have their money machine, the debit machines or credit card machines, connected to the network. So when somebody wants to pay with a credit card or a debit card, they just swipe or tap or do whatever they have to do. Then the transaction happens quite fast. Bang, that's done, right? Next client. Well, what happens if the network goes down? The network goes down, then, well, there's no connection to the VPN. If no connection to the VPN, then all the cash registers are shut down. No transaction can be made because there's no connection between the mainframe of the whatever the corporation is. So here's a solution to that. If the network goes down for whatever reason, there is a backup dial-up modem. And if the store has 6 cash registers, 6 POSs, which is point of sale stations, 5 of them are going to be shut down, and there's going to be one 6th one designated, chosen and designated as the kind of a fail over type of thing. So that was going to remain open. However, when the transaction is being made by the money machine, and I don't want to use any brand names, then this dial-up modem kicks in. It dials the server of the financial institution or financial server, makes a transaction, hangs up the phone. It works much slower, but at least you can keep the sales going. So that's how, and sometimes you're going to have service calls when you're going to have periodical verifications if that thing is actually intact. So you're going to go to whatever the store as an annual maintenance and say, okay, during some, less busy hours, and you're going to shut down the network and see if this one kicks in properly and makes a connection, and then you're going to get some confirmation from whatever company is providing that service, and you're good for another year or 6 months or whatever the maintenance period has to be. So yes, dial-up modems are still being used. So you can buy a nice US robotics modem, brand new one still. Right? Now, are we done with this? Yes, that's the end of this presentation. Yes, a couple minutes over time. And just look for the information. I'll send this by email about the online test that we're going to have. And I will see you when I see you. It is Friday. Please enjoy your weekend. Stay healthy and safe and all that philosophical stuff. Thank you, guys and gals. I'll see you when I see you.